So we know that the electric field as measured at the point P above this positively charged rod is supposed to equal simply the integral of the differential electric field elements in the y direction, j hat. And again, that's because of the fact that all of these differential electric field elements in the x direction, they end up canceling out with each other. And again, there's obviously many, many more electric field vectors, DEs, which have their own individual components all throughout this rod, but they end up canceling out with each other is the idea. And simply, the electric field at the point P should be equal to the integral of all those tiny little differential electric field vectors in the y direction. Which would make sense because obviously that would put the electric field to be in the j hat direction, the positive y direction, which would be upwards and away from the positively charged rod, which makes sense because positive charges, or light charges repel, right? So anyway, this is the situation we're at. And we know B is constant. B has been defined for us because of how we define the pointer here, but we do need to know what R is. We defined R here, but what R represents? R represents the distance from where we're measuring the electric field to be at, which is at the point P, to any place along this rod, this positively charged rod. That could be over here, that could be over here, it could be anywhere in between. There's a point where R might equal B as well. But we're going to end up writing R, because R will end up equaling the square root of, we're going to write x squared plus b squared. Because that comes from the fact that we're dealing with Pythagorean theorem. This is a b, a length of b, which is constant. This is some distance x. We'll call it x right here. It's just some distance along, x is just some distance along this positively charged rod. That's all x represents. So, it still makes whatever it is though, whatever that distance x is, it makes a right triangle, so therefore R, we'll call the hypotenuse, which is the distance from the electric field, we're measuring it to be onto wherever point of the rod. R thus equals Pythagorean sum, square root of x squared plus b squared. X squared plus b squared, square root that is R. Okay, we have that. We can at least rewrite the integral sum. We can thus write, we can pull the b out because we know the b is constant, right? B is constant. Now we're integrating 1 over r. Now we know r to be equal to the square root of x squared plus b squared. Now we still have this differential electric field right here. What is that? I mean, we said dE sub y was equal to b over r dE j hat. I mean, what is the differential electric field for this thing right here? What even is that? I mean, right, what is that exactly? I want to resort back to how we define an electric field in the first place. So, we said right here that the electric field at the point P is equal to 1 over 4 pi epsilon naught integral dq over r squared j hat. This is what we said. This comes from the AP Physics C formula chart, but this also makes sense in general because we said, hey, electric field in general is electrostatic force over test charge. That ends up simplifying to kq over r squared. I mean, you can integrate dq over r squared. Kq over r squared, you see the similarity there. R hat. So that exists. Now, how do we find the differential electric field? That's really what we're struggling with here. Imagine if we took the derivative of both sides of this equation, perhaps. I mean, let's write this. Let's write the differential electric field anywhere. This differential electric field anywhere should equal 1 over 4 pi epsilon naught, permittivity of free space. We're not integrating though. If we take the derivative, I mean the derivative and integral operators cancel each other out because they're like basically inverses of each other. So if I differentiate this side, and I differentiate this side, the derivative operator and the integral operator cancel each other out. So really we're just left with dq over r squared. Now let's actually make that the magnitude of the electric field vector, differential electric field vector. Let's just say that, because then we'd have a j hat, but we already have the j hat there. This right here comes from this right here, which we said it must be true, which we know to be true here. Basically, we're just imagining if we take a little, rather than the whole entire electric field at the point P, what if we just took a differential electric field? That would equal 1 over 4 pi epsilon naught dq over r squared. And that's what we're going to substitute in here for the differential electric field here. So I'm going to write, this is b integral 1 over r, that was what r was, times the differential electric field, which is going to be 1 over 4 pi epsilon naught dq over r squared. And remember, this is still with respect to, or not with respect to, it's still in the j hat direction, the positive j hat direction, right? So this right here is our integral, and we're trying to set this up. We still have a couple things we need to do though. Also, I'm gonna change what I just wrote here for square root of x squared plus b squared as r. I'm gonna change that back, and you'll see why. Oh, but you know, there's a whole lot of stuff we could do here, so why don't we factor out the 1 over 4 pi epsilon naught for one thing, take it out of the integral, because 4 pi, these are all constants. Electric permittivity, that's a constant. We can pull those all out. So really this would equal b, I'm going to pull the b out, over 4 pi epsilon naught. So I took out b, I took out the 1 over 4 pi epsilon naught. Now we're just integrating now 1 over, I'm going to change this right here, square root of x squared plus b squared, back to r. You'll see why in a minute. dq over r squared j hat. It's getting kind of messy, but let me separate this. We know r, we know all this stuff. The only thing we don't really know right now, which they didn't really define in the problem, was dq. Hey, we found an expression for dq previously because we knew it was a uniformly charged rod, so it had a linear charge density lambda, which equals q over L. So we formed a differential. We said that therefore, because of how we define linear charge density, we know that lambda dx should equal dq. So let's substitute what that is back into this equation here. Let's see what happens. So really, we're going to end up getting integral b over 4 pi epsilon naught integral, by the way, I'm going to multiply this r and this r to make it r cubed, 1 over r cubed dq. What's dq? Lambda dx, we said, right? And then we still have positive j hat. Now, lambda is supposed to be constant, though, in this integral, is it not? Lambda should be constant, right? Because it's linear charge density. It doesn't matter. It's supposed to be a constant, whether I'm dividing the total charge by the total length of the rod, or a tiny little charge of the rod by a tiny little length of the rod. Lambda should be constant, so we can pull it outside as well. So really, we end up getting lambda b over 4 pi epsilon naught integral 1 over r cubed dx j hat. Now I'm going to substitute what I know for r now, just so we can see what's happening. This equals lambda b over 4 pi epsilon naught integral 1 over, now r we said was equal to this square root of x squared plus b squared. So basically x squared plus b squared raised to the 1/2. Cube that, you end up getting x squared plus b squared raised to the 3/2 power because of exponent rules. We're integrating with respect to x still. So we have the dx, differential x, and then j hat. That's still the direction here. We are basically ready to integrate, but there's one thing we need to do, and that's bounds. I mean, this isn't really going to be useful without bounds of integration. We need to have some bounds of integration. But what are we going to use for bounds, though? What are we going to use for bounds, right? Now, in the problem that I'm working with, this is defined at this point right here, like right in the middle of the charged rod. This is defined to basically be not x equals 0, but because x equals 0 is right here, technically. I guess it's sort of defined to be 0. then what is we'll just say this, that this is negative a. So if this side of the rod is negative a, this is just putting like some basic coordinates on it. This is 0. Then you might think, okay, this is positive a. I'm actually going to rewrite it though as like L minus a. It's not entirely necessary. It's just the problem that I'm doing has that. But it makes sense because this is the total length of the rod minus a, which is this, L minus a, should equal this length right here, right? The whole entire length of the rod, L, minus a, should equal L minus a. That means negative a, 0, to a, you could say, or, you know, L, the whole length of the rod, minus a. Those are going to be our bounds of integration. And with that, we will now be ready to integrate. So lower bound should be negative a. Upper bound should be L minus a. We are ready to integrate now. This is exactly what the electric field at the point P is equal to. Messed up my bounds. This is literally the electric field at the point P. There's nothing more we need to do aside from integrate. All of our notation is correct. This is literally the integral now. Let's get out some new paper. So we're saying that the electric field at the point P is equal to lambda, linear charge density, or B, lambda B over 4 pi electric permittivity of free space, epsilon naught, a constant, integral, we're integrating from negative a to L minus a of 1 over x squared plus b squared. I'm gonna rewrite this with a radical, just because it's gonna make a little bit more sense, I think, if we do that. Just cube the whole radical. It's the same notation as right here, and then dx j hat, because we know the electric field is supposed to be in the positive. The electric field at the point P should be in the positive j hat direction, because again, I mean that makes sense. You know, like charges repel the direction a positive point charge move. That's how we define the direction of the electric field. A positive point charge move away from the positively charged rod. So of course, positive j hat direction. Now we are ready to integrate. We are ready to integrate. How do you integrate this? And perhaps to make this a little less cluttered, we should move this off to the side for a minute. Let's just consider the basic integral for a minute of 1 over square root x squared plus b squared cubed, whole thing cubed, dx. Ignore all the notation and everything. Let's just consider this. How do you integrate this? I see in the denominator, I see a radical. It has an x squared plus something squared. When I see that, my mind immediately thinks of integration by trigonometric substitution, trig sub. It's the perfect opportunity to use here. So, again though, we have like in the denominator, we have a square root of x squared plus b squared. The way I like to, so, I mean, this is kind of like the same format, you know, as square root of, okay. Okay. This is kind of the same format as the square root of b squared x squared plus a squared. Now, this is the standard sort of, whenever you look at like a table of like integral rules and you see trig sub integral rules, you usually see like, okay, if you have an integrand which has a radical term like this, it's usually expressed as like square root of b squared x squared plus a squared, or like whatever other combination, like x squared, you know, b squared x squared minus a squared, or whatever. Whenever you have this specific format, though, you're going to need to use, well, you want to, trig sub. This implies x is going to equal a over b tangent theta. This specific format implies that x equals a over b tangent theta. Why? Because we see x squared plus something squared. I mean, we know from the trigger entity, one of the fundamental Pythagorean identities, we know that 1 plus tangent squared theta equals secant squared theta. So, kind of similar argument going on here inside the radical, right? Normally, whenever we see something like this, whenever we see an integral like this format here, we should do x equals a over b tangent theta. We have a similar sort of integral here. So the square root of x squared plus b squared, well, that should imply x equals something. What is x going to equal? A over b? Well, in this case, the a is the b. It's kind of confusing. It's just a is supposed to represent the constant out here, which in this situation is b. So b over 1 tangent theta. X should equal b tangent theta. That is what actually equal. Now, if you do enough trig substitution, you know that therefore you need to also form the you need to figure out, take the derivative essentially, but form the differential at the same time. Dx must equal b. If I take the derivative of tangent theta, I get secant squared theta. Then forming the differential, we have to put the d theta on here. So we can rewrite square root of x squared plus b squared simply as equal to, substituting in what we know, square root of x, b squared tangent squared, because we square x, b squared tangent squared theta plus b squared. Don't need the parentheses there. I can factor a b squared out times 1 plus tangent squared theta is now what we have. Now we know because of the trig identity up here that therefore 1 plus tangent squared theta simplifies to secant squared theta. This really equals the square root of b squared secant squared theta. Of course, if I take the square root of both of those, I end up getting b secant theta. So this is what the whole square root of x squared plus b squared actually equals. B secant theta. Okay. So let's go back to the original integral that we were trying to do here. We can thus rewrite it as equal to integral 1 over square root of b squared plus x squared plus b squared. That's b secant theta, cubing all of that, so we end up having b cubed secant cubed theta. And then we have to put the dx, which we know is equal to b secant squared theta d theta. Doing a little bit of algebra, we know that this secant squared theta right here cancels out with secant squared theta here, and also one of these b's cancels out with one of these b's, which makes it b squared. So really we can factor out a b squared, or we can take it outside the integral, so we really end up integrating 1 over b squared. That's outside the integral. Integral, got rid of this, we got rid of this. We're just really integrating 1 over secant theta with respect to theta at this point. Of course, that just equals cosine theta. We're integrating cosine theta with respect to theta. Of course, that just equals sine theta. This really equals 1 over b squared sine theta. I won't worry about the bounds of integration right now because I already know we have the bounds of integration up here we need to worry about. We have this. Of course, we need to fix this because I don't want to be using sine theta. I mean, we were integrating originally with respect to x. We could change bounds to theta if we really wanted to, but that might make things confusing. Let's just stick to x. Let's convert what sine theta was back to something we know. Now, to do so, you need to do the triangle, the famous right triangle. Let's draw a right triangle out. Let's call this angle theta. Now, previously when we did the trig sub, we said that x equals b tangent theta, right? That is how we did this trigonometric substitution. Well, therefore, it follows that tangent theta simply equals x over b, right? Now tangent theta is equal to opposite over adjacent. So if tangent theta equals x over b, that implies that opposite equals x, and adjacent to theta is b. That would therefore imply the hypotenuse is the square root of x squared plus b squared by simple Pythagorean theorem. So what is sine theta then, according to this triangle? Sine theta will equal, therefore, opposite over hypotenuse, which is going to equal x over square root of x squared plus b squared. Okay? That's sine theta. So why don't we replace that? This equals 1 over b squared sine theta x over square root x squared plus b squared. And that right there is our integral when you do this integral right here. So we integrated. We're not done yet though. We're not done yet because that was only half of it. We have to resort back to this definition though. So I'm going to rewrite this using what we know. Because we said the electric field at point P was equal to all this right here, I'm going to rewrite it and say that the electric field at the point P now is equal to lambda B over 4 pi epsilon naught. That's still out there. Constants. You integrated this though, you knew we ended up getting 1 over B squared times x over square root x squared plus b squared We're evaluating this from negative a to L minus a, so we have these vertical bars here to demonstrate that we're evaluating. Negative a to L minus a. Of course, there's still a j hat, though, isn't there? Of course. Well, really we just need to evaluate. This is all we need to do, but before we do that, a little simplification. We know that because we have b right here and a b right here, one of these cancels out. This b cancels out with this b, so really you can simplify this to just equal lambda over 4 pi epsilon naught. Of course, put that b out here as well. Lambda over 4 pi epsilon naught b times x over square root x squared plus b squared evaluated from negative a to L minus a. This is what we have. In the j hat direction, of course, because again, electric field goes in the positive j hat direction, which makes sense because the like charges repel. The direction of positive point charge move is away from the positively charged rod. Like charges repel. Positive j hat direction. Let's evaluate this separately without using that, just so we can make this thing a little bit simpler. X over square root x squared plus b squared evaluated from negative a to L minus a. How are we gonna, with that we just plug in for what x is, right? So this really ends up equaling x, and the x on top becomes L minus a over square root of x, which is L minus a squared plus b squared minus negative a over square root of, let's see, negative a squared becomes positive a squared plus b squared, let's call it that. Simplifying this becomes equal to L minus a over square root of L minus a squared plus b squared, squared all that, plus a over square root a squared plus b squared There's not really anything else we can do at this point, to be honest. Like, You can get a common denominator, but no, that's not. That's we don't need to do that. That's not necessary at all. So, and from here, all you need to do is simply sub this back in. What we end up getting is lambda over 4 pi epsilon naught b this evaluated became equal to L minus A over square root of L minus A squared plus B squared plus A over square root A squared plus B squared. That whole expression, all that times lambda over 4 pi epsilon naught b. Last but not least, the j hat vector. That right there is going to be the expression for the electric field at the point P. This is our final answer. This is both the magnitude and the direction, because it has these formal vector notations. Quite a bit, but again, should go in the positive j hat direction, because we know that the electric field goes in the direction of positive test charge remove, like charges repel. So a positive test charge remove away from the positively charged rod, so therefore it should go in this direction. And this is our answer right here.